Hi there, Michael.
Hello.
Hi.
There you are. How are you, Brendan?
Yeah, doing all right. Still breathing.
That's good.
I just got a message from Paul. Did you see it? He said he's going to be late.
No.
He says he's going to be late attending.
Okay. I think maybe you only received that message.
Yeah, I think he just sent it to me. But,
how
are you?
Okay. Doing pretty good.
Okay.
Yeah. Looks like you've been making a lot of progress this last week.
Yeah, I've been making bits. Although I'm for the last day and a few days, I'm just stopping doing any academic work at the moment, just for a few days, because I'm trying to prepare for an interview. I just need to freshen my mind up a bit in astrophysics at UCL. So
okay.
Hopefully doing some work there,
That'll be a little bit of a change of pace from the magnetic resonance.
Yeah, magnetic. I mean the magnetic induction tomography is what I was doing before. Tomography using magnetic fields to image inside metal boxes.
Yeah. Yeah. So you're instead of looking inside the box, you're looking outside the box.
Yeah, that's right. And I might have to put my astrophysical political hat on because they're into black holes and Big Bang. You see, so I have to be careful what I say.
Well, that's right. Well, I guess ultimately, it's just a paycheck. So.
Yeah.
Yeah. Although it would be nice to be able to get paid to do research that you can get behind.
Yeah, it's interesting. Have you heard of the inverse problem before?
Well, it depends.
It's a kind of like it's quite a sophisticated form of mathematics that engineers and physicists and climate scientists use. It's used a fair bit, although the field of inverse problems in mathematics is a sort of small field.
Is that like in terms of matrices?
Yeah, matrices. It's like if you've got a ring of coils around an object, you're imaging inside it. You just take the readings of the voltages in the coils and the phase, and then you have a forward model, which is Maxwell's equations you simulate it with just a guess answer, and then you take the readings of the voltages, and then you take the inverse of the forward model, which is basically is a simulation of the setup, just a pretend simulation. You take the inverse of that forward model, and you can get say the conductivity of the objects inside from that. And it's reasonably sophisticated mathematics.
So you're not going to go into what do they call that field where you search for secret treasure?
All right, yeah, they can use it for that. So magnetic induction tomography is the same principle as the metal detector.
So yeah, I hear they have space-based systems doing that.
You can use it if you've got a special kind of inverse algorithm in your metal detector. You can tell whether the metal under the ground is gold or silver or copper, because it will have a different conductivity.
And can you do that from space?
Yeah, you can do. They can use inverse problems, all kinds of things. For space, they can use it. You can make gravitational field measurements of the surface of the Earth, and then using the inverse problem, you can find the density regions of the Earth, not just the Earth as one average density, but the density regions. And they're using it in the work that I'm hopefully going to do. They're using it in to model to image inside stellar clouds to where stars are being born, and they can get all kinds of readings like pressure, density, radiation rate using the inverse problem and Monte Carlo, Bayesian statistics and Monte Carlo. The Monte Carlo, to my knowledge, is just like when a problem's too difficult to solve by normal methods, you can cheat a little bit and use the Monte Carlo method, which is where you use random points on the curve to get the area under the curve, like integration. So it's a bit like using a little bit of a cheating method when the solution's far too difficult to solve by normal methods.
Huh. Well, that sounds pretty interesting. Who's is it going to be for fundamental research?
Sorry,
will it be fundamental research in terms of
if I get it, if I get the work,
yeah,
and then it will be for it's Professor Serena Vitti at UCL. She's head of astrophysics there. We're working for her, and it will basically be her speciality is star formation, star birth and formation in galaxies.
Are you going to be looking at Jupiter at all?
Well, not unless I watch a documentary. So anyway, but they know the inverse problem. I know it about 50%. I haven't, but I can learn about it, and it's easier to learn about it if you're working with people who know it anyway. If you're working in a group where they don't know it but they want you to know it, it's pretty tricky to learn because you go on courses and things like that. And
oh yeah, well that's how it goes with most everything.
But you can use the inverse problem to get out information from the clouds, like radiation rate or density or temperature or chemical species and things like that.
And it doesn't really have anything to do with like mission lines or that type of things. Is more magnetic than anything else. It works on magnetic readings for the most part.
What does? You mean the inverse problem? Inverse problem can be applied to lots of different things, lots of areas. It can be used in magnetism, tomography imaging. It can be used in it can be used in acoustics, sound, acoustic imaging under the sea, under the rocks, under the seabed. It can be used in gravitational field measurements. It can be used in all kinds of different. You can just so it's a technique that you can apply to many different types of problem. And
well, that sounds like that could be a rewarding job.
Yeah, that's right. That's right.
Yeah. Are you interested in actually getting into academia yourself as a professor or anything like that eventually, or are you more interested in independent or private type things?
I'm quite interested in getting into academia. I've been in academia. I did postdoctoral work, and I did a honorary research associate, which is like another type of postdoc. Postdoc is postdoctoral after doctorate.
Mm-hmm.
And that's the first bit. But after postdoctoral, they usually do about 2 or 3 places in different universities as a postdoc, and then go on to a lecturer, and then senior lecturer, blah blah blah.
So that's pretty much the track that you're on.
Yes, I have to. I'm basically just trying it out. So I'm doing it a bit. I'm doing it on a voluntary basis at the moment, so I'm not being paid, and I'll just have to see how it goes. So that's one way. That's how I can get into it, is by if they had to pay me, they'd probably get someone better.
Huh.
So
well, that's kind of hard going. I mean, to be able to pay the bills and all.
Yeah, I got, but I'm okay. I'm secure. I'm relatively secure financially, so I don't have to worry about that at the moment.
Oh, good. Yeah.
Are you done? I was going to ask. Go on.
Pardon?
I said. Were you going to say something?
Oh, not particularly.
I thought of something today or yesterday, I thought was an interesting, a sort of fundamental question to ask Paul Laviolette, and that is, I'm sure his answer will be. I'm not sure what his answer will be, but one of them is: do we need spin for subquantum kinetics? because subquantum kinetics is quite different from quantum mechanics. Quantum mechanics has got spin involved in it, because subquantum kinetics can predict a fair bit already. So is it of fundamental importance to have spin? And that, I wanted to ask Paul that, because I think he might be interested in his answer. I'm sure his answer will be yes, we need it because it's shown in quantum mechanics. Like we were talking about the Stern-Gerlach experiment, where it deflects. It goes through the Stern-Gerlach magnets, then deflects, and that deflection, according to quantum mechanics, is due to spin, the spin orientation of the atom.
It's possible that it could be due to something else.
Yeah, that's right. And so I'm thinking, if subquantum kinetics is quite different from quantum mechanics, does it need spin? I mean, it works to a certain extent already. Does it require spin? And things like that. So
Well,
the next question I was going to ask, go on.
yeah, I mean, that's actually, I don't know if how well I came across before, but that was, I know that is, I can't speak for Dr. LaViolette. Of course, this is obviously the thrust of the research that he was interested in. But I was curious myself too, if that these type of let's say dynamics could be not due to spin, but could be due to like tail entanglements and things like that, or sort of like rotations instead. Because if you always have motion going on in the universe, there's always going to be relative motions. Once something's going to be passing past something else, and then they have effects on each other, which could then lead to rotational movements, and because of the way they interact with each other, and then that could lead into spin dynamics and that sort of deal. And then it could explain that.
I was just thinking with the model.
Gerlach experiment. Excuse me.
This map of this plot of the neutron with charge density.
Yeah.
One thing I was thinking is, I wonder if there's a conversion because the subquantum, because the plot that we're doing is very Paul's indicating a similarity here, which looks very similar. I'm just wondering, what is the conversion of charge density into etheron potential? There might be a conversion of the units.
I would expect so.
And also, if this relates to spin, then if we got say we wanted to know spin, if we got a particle like the electron or the proton, and we know from particle physics data it's spin angular momentum, we can get out of that the omega, the angular velocity, put that in our model, and then see if it becomes closer to what this is.
One thing that I know from so far is that I don't think we've come anywhere near modeling an electron. I think pretty much everything's been based on the neutron, which is similar to a proton, which is a soliton. So proton, neutron, soliton, so far has been shown to have very similar concentration profiles. One's electron density, the other one is reactant density, and they have very similar geometries. But I don't think we've even gotten into the realm of electrons yet.
Mm-hmm.
You know what I mean? Yeah, and it's possible. There's many researchers out there, or at least a handful, who believe electrons may not even really be a real deal.
Right. Okay.
Yeah.
Because it's so small. It can be similar to particle physics. Can be a bit similar to Ptolemy's astronomy. Do you remember Ptolemy, the astronomer from about 2,000 years ago? Greek astronomer.
That was a heliocentric astronomer,
Yeah,
right?
he had a model
No,
of
wait,
he had a model of the
Earth-centric,
first century.
Earth-centric astronomer.
Yeah, he was Earth-centric, so he believed, but he had a mathematical model that showed how the Earth and the planets revolved around the sun.
Yeah,
And it was so accurate, he could pinpoint.
you mean the Earth.
He could tell where the Hi there, Paul.
Hi. I'll be probably only about 15 minutes or so because I'm going to catch a plane tomorrow morning here in Bosnia. Also, the internet, I don't know how long it will hold. It's been going in and out. So
how was your trip, Paul?
Yeah, well, it's been here almost 10 days, and you can feel the energy there in the tunnels. I'm hoping it will raise my white blood cell count so that I can get whatever is left of the cancer. But it's it's been interesting. Not much to do except relax here. So I suppose that's good. So go ahead.
Seeing as you're going to be here for a short time, I wanted to ask a couple of questions. I think I know your answer to the first one, but I was just wondering, seeing as subquantum kinetics can predict a fair bit already, and that it's quite different from quantum mechanics,
Wait a minute, can predict what? I didn't quite catch it.
Can predict so like the predictions that you've given.
Yeah.
In like the I'm just trying to remember now. The pioneer effect.
Yeah.
The redshift of galaxies and tired light. So I was wondering, and all the others, I was wondering, is it necessary to have spin? I mean, is it because subquantum kinetics is different from quantum mechanics? Quantum mechanics seems to need spin of electrons and protons. But is it possible that can subquantum kinetics work reasonably well without it, or does subquantum kinetics need spin? And is spin the same as?
Does it need the Schrodinger equation? I don't know. If physicists are stuck on that, it would be nice to have some version of it that would show there's a different interpretation of the wave-particle experiment.
And the other one was: is there a way? See this plot of the neutron here that's giving similar kind of shape to the one in that we did.
Yeah.
Yeah. See, similar shape to this one here.
Yeah.
Okay. What I was wondering, is there a conversion? If this is indeed showing something similar, would there be a units conversion from this X, Y, and G potentials to the charge density?
Yeah, there should be.
There should be a conversion between the two.
Yeah, I haven't gotten that far to putting in, it's mainly just trying to simulate to get the right forms, I guess. But how you would get those dimensions to be the same in the simulation, I guess, is
and also gone
scaling the concentration, however you define your cell dimensions, I guess. But that you can do later, to equate the cell dimensions with real dimensions.
One of the things I was thinking about was this again at this plot of the neutron. If we looked at the spin of a neutron, angular momentum, we could take the omega, the angular velocity from that spin, and put it in the model, and maybe the model will look even more similar to this one here. Is that a possibility?
Well, remember that these are due to particle scattering experiments, and so it's a question of how that would relate to the actual form of the particle. You know, this is the way they're inferring it from their scattering results. And it's what I think is interesting is that the first well outside the core is about like the same dimension as the radius of the core in both cases.
So that's the radius of the core being this bit here,
Yeah,
radius of the core of the neutron, right? So this bit here and this bit here, similar to the radius, or that bit from that bit there, the similar as the radius of the core of the neutron atom, neutron particle.
yeah. Well, this well outside the core, the width of that is about like the radius of the core, approximately. But to put in spin, I think we need to do 2 dimensions at least. Doing a spherical symmetry won't work, I don't think.
I've one of the things I updated these notes I was making of the progress. They're on the. I can send you a copy if you like, but they're on the Facebook page. This here. So this here is the partial differential equation for the geon here.
I'm getting a message that my internet connection is unstable, so I hope I will still be here anyway.
Okay, so,
go ahead.
So that's basically, so what I've done is I've done a conversion. I've just changed these bits here to G just to make it able to me to work with the symbolism more easily. Just a temporary conversion.
Okay. Normally G is concentration, but
yeah,
interpreting here as
So I'm just saying that those are the same. I'm just making that temporary exchange to say those are the same, in order to avoid confusion in the symbolism. And this is basically the Crank-Nicholson solver. Takes this bit here to be like that. It slices up the equation, and these are the approximations, and then it goes into this form here, out of which you obtain the matrix for programming.
Okay.
So David says that in the email he said that he would try and he would, after his new customer, he's over with his new customer this week. He's going to try and program the Crank-Nicholson solver to 2D, 2 dimensions.
Great. Now, as far as computer time, have you gotten an answer from Amazon?
Is that you, Michael?
Oh, unfortunately, no reply.
Okay.
Mm-hmm.
There's a fellow here, in Prague, who is billionaire, actually, mathematical genius, I guess you'd call him. He made his money by designing buying and selling of the market, and I'm going to try to sort of feel out whether he might be interested to help us out. He might even be able to help out with computing time. Maybe he has his own. I would imagine he uses some mainframe for his work. He must have some funds that people invest in or something. I'm not sure yet. But anyway, I'm trying to look into that too.
Yeah, that's the amount of funding needed for this project for him. It's pocket change, and not even that, you know. Yeah.
Well, he's open to new physics, which is the important thing.
Mm-hmm.
He's funding the experiments that we'll be doing in Prague to test some of the subquantum kinetics predictions on superluminal wave velocity and time dilation and other things.
Is he new money or old money? Pretty new money.
Excuse me, what?
he made his own money, right? He's pretty new.
He started from zero. He designed a program that was better than other people's programs, I guess, and he was able to beat the market.
So he's probably an independent person with yeah, he's willing to back up some radically different projects. That sounds, yeah, absolutely.
Did you say he was a billionaire, Paul?
Yeah, well, he became a billionaire. He's fairly young, actually. He's in his early 40s, I guess.
About my age.
Yeah.
So another option could be to
we could invite him to, if he wants to come to our group. We'll see what he says.
Okay. Well, do you want me to put? Is he on Facebook? Do you want me to give you his name, so I can put an invite on the up here? This one here is invite.
Oh.
So
well, I could send his. What do you need? His email address or something?
What about his name? Oh, hang on a minute. There may be someone.
Well, let's first find out if he's interested.
Okay.
I can send it to you.
So another option is actually, because Matt has written this Mathematica code. He's done a 2D version, which took a long time, which took, I think, about a week or something to run, and it filled up it overloaded his computer.
Well, that's you're pointing at the 1D.
The 1D and 3D. Yeah. So these are in. So this is a symmetry of 3D using spherical coordinates, and this is using Cartesian coordinates in 1D.
Did you find the same thing? It filled up your memory to run 3D?
No, this one here takes about. They both take about 10 to 20 seconds. I said 30 seconds here, but it's more like 10.
So why do you explain the difference? So I mean, what do you?
3D. He says in the paper that that the 3D is just a symmetry. It's just he just used one dimension, but he used a symmetry in spherical coordinates.
Yeah.
Whereas this 1D, so that he's saying okay, if this is symmetry in spherical coordinates,
okay,
then 1D
but
must be like a slice.
It filled up his memory.
Because that's what I was asking him about originally when I sent him the email. I was asking how come this 3D takes 20 seconds to run.
I believe that was probably not with the spherical symmetry, I would presume.
Well, this one, I looked it up more carefully. This one here is done in Cartesian coordinates, and this one here is done in spherical coordinates.
Right, but the one that would take up all the memory would be for the 3D without.
Yeah, the 3D. The 3D, the 2D would be like a surface plot in 2 dimensions. So you've got the z-axis will be concentration, and the x and y will be position.
Yeah. Right.
And
he's have you seen the 2D plots? Sort of, but I
asked Matt for the code for the 2D, for the proper 2D plot, and he said he wasn't sure when he could find time to find it. But if we can get that,
we have the 2D plots are posted on YouTube if you want to see them. They look like Atlantis.
All right. Do you mean the one is that with Mathematica or ETD Stepper?
Well, I assume he used Mathematica for everything.
Because we've got one down here. Let me just find it. ETD Stepper.
I think he used to keep it on his Blue Science website, but I'm not sure if he still has that up.
I have them on my laptop, some of the 2D plots.
That's a 2D plot.
Yeah.
ETD Stepper.
Hmm.
But I don't know, is it X, Y, and geons, either one, or is it all 3? I wasn't quite sure about that.
Well, he had some 2D plots where the z-axis showed concentration. It was sort of a perspective view, like looking at a cube. This is like looking down at the top, so you don't see the z-axis.
So when we do two-dimensional, we may have to plot X, Y, and G separately, because otherwise it may be a bit too confusing on a
Yeah.
let's have a look. So so that's in Mathematica, and he's done 2 dimensions in Mathematica. So it may be easier to input the velocity term into Mathematica, because it's a bit more simpler to understand, to explain it. I think there's 2 ways of solving equations, partial differential equations. One is implicit, and the other is explicit. Implicit means you solve the equation, get the answer. Explicit means you approximate it using numerical analysis. So anyway, he may, if he gets round to it, he may send me the 2D proper version, and I can have a look at it. Otherwise, I'll have to try and develop it myself.
You mean the graph or the code?
The code that produces this in Mathematica.
Okay.
By the way, I've got I may have a new job coming up, Paul. In astrophysics at UCL. So I'll have to see how it goes in astrophysics.
Okay.
And so at UCL, so I'm just gonna, in the next few weeks, I'm just preparing reading. It's on star formation. Can you hear me?
What do you mean star formation?
Well, it's just it's a bit of voluntary work, and I'll see how far it takes. But so it's with UCL astrophysics department.
Oh, I see.
So I'll with the.
By the way, one of the projects which it would be interesting to do is take the equations they use to simulate like Jupiter, the heat inside Jupiter, or inside a brown dwarf, and then just add to their equations the genic energy relation, that energy is not constant, but it increases over time, and see how that changes their model. And I would guess that it would end up explaining a lot more things than what they're doing now.
Do you believe that Jupiter is a budding star, Dr. LaViolette?
Well, it's
proto star.
Yeah, it grows. If Jupiter grows, it will grow into a brown dwarf, and if it keeps growing, it will become a red dwarf, and then a sun star, and so on. So right now, it's the heat from the Jupiter is just genic energy, mainly. It's baloney that it's due to the collapse, the heat of collapse. It never did collapse. It's been growing from the time it was a little ice asteroid in space, and it's just been accumulating gas and growing, and also producing some of its own matter. So.
Right. That's why when Brendan brought that new job up, I asked them if they were going to look at Jupiter. The same thing. Yeah.
Well, they do extra exoplanet observations by analyzing spectral data. They look at the planets in other star systems.
Yeah, what I'm talking about is modeling the interior of the planet, like it's the temperature at different depths, and the density and the pressure, all this.
That would be perfect for that type of work. Yeah.
I mean, it's such a simple modification. For years, I was trying to ask people that had the program, would they mind letting me use it or something. They just weren't interested in help at all. I mean, it was really pathetic. I mean,
they didn't want to share their toys, did they?
I have to be careful what I say about, I have to put my astrophysical political hat on. So I have to be careful what I say about black holes and the Big Bang. So I think because their politics is that they have to believe in that, and go along with it. So I have to be careful what I say.
Yeah, right.
But they're using the inverse problem to get to look at things like to calculate or to model or detect things like different properties like ionization rate, density, and chemical species, spectra, chemical species, and that kind of thing. So,
well, yeah, don't get off the track. But if you find an opportune moment to bring it up, you could ask if they have that kind of software to models.
Yeah, models a planet, the core of a planet, the inner core of a planet like Jupiter.
Yeah.
Okay.
The heat flux and stuff like that coming out of the core. Yeah.
Okay. Well, let's just. So basically, Matt's got the 2D version for this, which I hopefully he will send at some point. He just said in the email that he was he won't know when he get round to looking for it.
Or maybe he's trying to just say he doesn't want. He's put in too much time already. He doesn't want to put any more. I don't know.
Yeah. I think and also considering he's the one who knows the most about the project work.
Yeah, it's too bad that he doesn't have the time or doesn't want.
We can do it ourselves. We can work it out. We can work out. I can work out from this. I'm saying I can do it. I'm just putting it out there. I should be able to work out how to change that to 2 dimensions. And then as David Johnson was saying here, how long would it take to do 3D? He said, I said it took about 10 to 20 seconds.
Well, Mathematica has some pretty good experts. Have you ever thought of talking to them?
Yeah, that's what I was saying to Dave Johnson, that we could, the Mathematica license may allow us to put this on the cloud, on their mainframes, and then.
No, but I mean, they might give you some ideas of how to go to 2D.
Yeah. That's a question to put to Mathematica Forum or Stack Exchange, Mathematica Forum as well.
It depends on how good a support they have. I mean, we used to do that all the time in business. We bought a product, and then you call up and ask to talk to their chemist, and they give you all sorts of great advice. So it all depends on the support level.
Yeah.
And also to call up they've charged me twice for it because they had a problem with the credit card. They've charged me twice on my account, once from my debit card, once from my. So I have to phone them up on Monday. Mathematica.
Clear that up.
Yeah, to clear that, so they don't charge me twice for it. Yeah. So what I could do is I could phone I could send an email to Mathematica and ask them questions about how we could go about doing this. With the running. The other option, Paul, is to go on Stack Exchange, to search on the net and ask a question on Stack Exchange Mathematica.
Yeah, good idea.
So I think so. So this is the Crank-Nicholson solver is another method, and that doesn't I showed here. Basically, it's Crank-Nicholson method. Here it is. Here's an example of a partial differential equation, and nonlinear terms here. They've broken the equation up into with respect to time and respect to distance and the constants, and then they've arrived at this equation here. When they put these together to make it in this form here, they've arrived at this one. They split it up a bit more, and then down here they've just put it into matrix forms, and that matrix form is what one has to convert into programming, i.e. C++. And that's what Matt has done for the C++ version. He's taken something a bit like this, and that equation there is obtaining the quantity. In our case, it's ether on potential by solving these matrix forms. And then you can get the etheron potential at each time point. So J here represents time. So J plus is the next time, and J is the previous time, and I here and I plus 1 or I minus 1 represents the x-axis. So to put this up into, this is 1 dimension. To put it up into 2 dimensions, we need to use this method here, read a bit about this here, and use this method here, which is the alternating direction implicit method. So to read through that and understand, so that's what I think that David Johnson will have to understand, work out from something like this, how to do it into, because it's saying here that it becomes extremely complex using the 1D method, something like that, to do it in 2D, using the method of 1D to put it into 2D. I think they're saying here.
Now this, can you email all that to me so I could send it to this fellow? And
yeah, do you want me to send you what about the video? So this is the rotational reaction diffusion academic note that I wrote, and it's got a kind of like
yeah, something as an introduction to what we're doing, so he could get an idea of what we're doing.
What I could do, Paul, is I could send him this one where I've just basically just outlined the Crank-Nicholson solver, and I've talked about ETD stepper. They're mainly, I've taken sections from Wikipedia. So
I'll see if he's interested in it. If he is, send you his email address and you could send those to him.
Okay, I'll send this one, and also I'll send the first report we did when we in the early stages, because that's more of an introduction.
Okay, I better, is there anything else? I think I better get back to packing.
Okay. I think that's all for the time being. And okay, so and we'll see how David Johnson gets on with the Crank-Nicholson solver later on.
Okay, great. Okay, well, so long for now, guys.
Okay, Paul.
Carry on.
Cheers,
Good night, Paul. And if you need any additional help, assistance with your health, don't hesitate to get a hold of me. I know people make cancer look like a walk in the park.
Really?
Yeah.
Okay, I'll see how I'm doing. I'll know in a week after I do my PET scan how well this therapy went and my immunotherapy, and how my blood cell count's doing. So
all right, I'll be praying for you.
Let you guys know next week.
Okay, I hope you get better soon, Paul.
Take care.
Okay, cheers and
bye.
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 Okay, Michael, do you want to call it a day, or do you want to continue?
Sure. I mean, the only thing I'd add is I did make a little bit of progress myself by I got my hardware working. So
okay.
Yeah. It's nothing super, but it's a spare device, so I don't have to interrupt any things I'm doing on my usual computer to run things on it. So that's nice. And so I might get something going on it, something simple, maybe this week. We'll see. But it won't be with Mathematica. So it'll either be ETD stepper or most likely ETD stepper, but maybe Octave. I don't know how easy it is to implement with Octave.
Implement with Octave, ETD stepper. You have to find out where he's outputting the data to. I mean, you could do Octave is kind of set up for managing plots quite well, 3D as well. So what you could do is you could have a look at ETD stepper, where the output's going, the X and Y coordinates and the Z axis for the concentration. You could find out where, and if you look at my GitHub page, do you know that one?
Yeah. Mm-hmm.
If you go on the Facebook and find my GitHub page, then you can look at the, you can find the way in the C++ code for the Crank-Nicholson solver. I adapted it to get the data out and put it in a file, and then with Octave I plotted.
Yep, I remember that.
So you can have a look at, you might be able to have a look at ETD Stepper, where they're outputting the data, get that data, put it in a file, and then plot it in Octave.
Okay.
And then you've got a bit more control over it than with the, you know.
Because I do remember, I think that was one of the steps involved was you could run 3D and it was already pre-programmed to output 3D plots.
Yeah.
But if you wanted to do one or 2D plots, you had to come up with a custom solution. Yeah.
And you could plot it with, you could do a scatter plot in Octave using surface plot. So it will just you've got the scattered data points for, say, so you're not going to do exons, geons, and myons together. You'll do them separately because it's too confusing in a two-dimensional one. So if you take out say the exons
for the plotting, yes.
The plot.
Yeah.
So if you look at my Octave code on my GitHub site, you can see how easy it is to get out the to plot the data. It reads a file and then plots it out.
I remember seeing your plots and all that. So yeah, I'll check that out. So
you just give me an idea of how to do. I didn't think of doing it with ETD Stepper.
Yeah, that's pretty much where I was a few years back. Was the computer I had was so slow, which is the same computer I'm actually talking to you on right now, that I couldn't get more than 1 or 2 snapshots out of the 3D simulation. So and then you had to do the plotting for the 1 and 2D, and I just got tied up with a whole bunch of other things, and you know how that goes.
We could also try a velocity term in with the ETD Stepper. You know, where you saw the equations plotted, you could just place it in there, even though you don't know what you're doing fully. You could just take the velocity term, put it in there, give omega a certain value, and see what happens. It might be as simple as you said it was, but you know, and if it doesn't work out, you realize then, okay, well, it needs to be adapted more properly. You know? Well,
chances are that this week, you know, if I get some work in, I'll probably just be running some basics, getting everything running. You know, yeah.
I think Crank-Nicholson is more straightforward to understand than ETD Stepper. But
maybe so. Yeah, it's quite possible. Maybe that might. Did the Crank-Nicholson software? It didn't have a plot.
I put one in. If you go to my GitHub side, you see where I've adapted the code to output the data.
That's the one I was thinking of. Yeah. Okay. All right. So I'll just get, because I really haven't been getting. It's been a while since I've actually gone in and tried running the code. So that's what I'll be up to.
I just take it step by step. Sometimes you won't understand what's going on. I was telling a friend of mine when I was doing PhD, one of my supervisors was saying to me, you know, most people doing a PhD don't have a clue of what they're supposed to be doing, even up to a year after the PhD, after they've started. They don't really understand what they're doing. And it's just the patience of the supervisor. You know, so sometimes you won't have a clue what you're doing or what's going on. You step back, let it go, throw it away for a while, and then when you're ready, you've got some new ideas later. It comes clearer later.
It's
step thing.
In a way, the process of science is not really always scientific. You know,
a lot of scientists have their breakthroughs when they're doing in a quiet time, when they're either sitting on the toilet or not even thinking about the science.
Yeah, there's these non-quantifiable elements going on there. That's for sure. Yeah.
When they're having a quiet moment of just like either meditating or just like not even thinking about it, then that's when the breakthroughs come.
That's it. Well, I think that's where you finally in a way, it's letting the mind, taking the mind off of this problem, and letting, in my opinion, letting the spirit have some influence, and getting some, sort of like Nikola Tesla. You know, he would get a lot of visions and that sort of thing. And
step by step, you work on. You have to do a bit of work from time. If you have to do some work, and you just
sure.
You put the work in, you step through it, and then you step back. But you don't work too hard, because then you're not going to get your bright ideas by just working. You put the work in when it's needed, and then you step back from. Then you get a lot of the time a PhD. When you start a PhD, often you come across something that seems to explain what you're doing to someone else, but it's very complicated. And you try to understand it, you can't really understand it because it's quite complicated maths. And that sends you off on a wild goose chase for about a year, trying to understand that bit there and that bit there. And then you come back to where you started, but it's much simpler. You know, so so at the times, because it gets so complicated, trying to understand what someone else has written about it, you have to let it go. You just have to let it go. And then when you're in a quiet time, you just, like, you throw it away, but not completely. You just throw it away. And then when you're ready, you don't throw it away completely. You just let it go. When you're ready, in a quiet time, then you see the answer. A new idea comes and you get it. You know?
But it's almost as if the idea comes when you're not thinking about it.
Yeah.
Yeah. Yeah. Well, have a great week, Brendan, and it was good visiting with you once again.
Okay, Michael. Take care, and I'll see you hopefully next week.
Yeah, and best wishes on your interview.
Thank you very much.
Mm-hmm.
Yes, then.
Goodbye.
Bye.